So these are the two methods here. The bottom one is the molar volume, which we just do one long dimensional analysis problem. The top one is the ideal gas method, where we stop at moles and then do an ideal gas law calculation. Which of these do you prefer? The bottom one? The molar volume method? Okay. We'll stick with that then.
So that would be the molar value for all gases.
For all gases.
Room temperature.
Yeah, at room temperature and 1 atmosphere. When you get to Chem 1A and 1B, a lot of our problems are just going to be at room temperature and 1 atmosphere. So this is going to be a lot more useful to know. Chem 1B as well. Obviously the temperature can fluctuate and the pressure can fluctuate. So it's not always at that. And so we only memorize one of them because it's the most common one. But what can happen is we can have different pressures, different temperatures, and if that's the case, we'll have to redo the calculation for molar volume. And so here is a problem where the pressure is 744 torr. Well, 760 torr is 1 atmosphere, so this is a little less than 1 atmosphere. The temperature is high, it's 131 degrees C. And so in this particular problem here, what we're going to have to do is we're going to have to recalculate the molar volume. And so we'll need the equation for molar volume here. So let's just go through here. And the molar volume is RT over P. And you just remember RT over P. But I don't like what Cartoligi does. He wants you to memorize a lot of different R values. So for example, he has a different R value for torr, he has a different R value for bar, etc. I just want you to remember one R value, and then if we're given torr, convert it to atmospheres. If we're given bar, convert it to atmospheres, rather than having multiple R values and just remembering those. It's kind of a hassle. And so I would have done this calculation differently. If you look at the way he does it there, let's do it the way I would do it. The molar volume, I'm going to do a composite, like kind of composite being sort of like what he does and what I do. R, I just remember one value of R, actually two values, but the other value we're not going to do until later. This is the only value of R that I remember. And so I got to just make sure everything works out. So I'm given 744 torr. And so rather than doing a separate calculation, I see, here. I see that the torr and atmospheres won't cancel. Do you see that? So what I'll do is I'll just convert it into the problem within itself here. That is, 1 atmosphere is equal to 760 torr. So rather than doing a separate calculation, I'm just going to combine it and do the conversions here. Just make sure the units work out. So in this case, the torr cancel and the atmospheres cancel. That's what we want. Okay, and then the temperature. What is the temperature? The temperature is 131 degrees C, which would be 404 Kelvin. And so here the kelvins cancel. And that leaves me liters per mole. Well, that's what I want, liters per mole. And so what do I get here? Let's do it. 0.08206 times 404. You should just double check that you're punching this in correctly. 744, and then I'm going to invert and multiply. So times 760. Wow, I'm way off. Let me try that one more time here. 0.08206. Oh, no wonder. 0.08206 times 404 divided by 744 times 760. So that's more like it. So I get 33.886. I'm allowed how many sig figs? I'm allowed 3 sig figs. So normally I might carry it like this, or I might round it liters per mole. They rounded it to 33.9 liters per mole. I probably wouldn't round it. I'd probably just carry that extra digit and round it at the end. All right, and so what do we have going on here? We have 16.2 grams of butane, C4H10. So what we're going to do is we're going to go from grams of butane to moles of butane, and then moles of butane to
Carbon dioxide.
yeah, and the moles of carbon dioxide, we're going to go directly to liters of carbon dioxide using the molar volume of the gas here. So let's go ahead and set that up here. So 16.2 grams of butane, C4H10. And then what's a molar mass of C4H10? Look up.
58.01.
58.01. 1 mole of C4H10 weighs 58.01 grams.
8 to 2 ratio.
Yeah, 8 to 2 mole ratio. 8 moles of CO2,
2 moles.
2 moles of butane. Okay, and then this here, which we could use either 30. We'll just use the. What should we use? I guess we should just use there 33.9 liters of any gas per mole of gas. So this one is generic. This works for any gas at this temperature and pressure. So it's not specific to CO2. And so let's see what their answer is here. So that's what they did, grams to moles, moles to moles, moles to liter. 37.8 liters of CO2. They got a slightly different molar mass here. Just double check. 4 carbons would be 48.04. And then 10 hydrogens would be 1010. I even got a different molar mass than what they got. I got 58.14. Well, anyway, it depends on how you round that as well. We end up with 37.8 liters, or roughly 37.8 liters CO2. All right, so let's take a look at some other problems that we might encounter in this chapter. Chapter 14. Okay, we can take a look at, for example, number 33 here. One source of sulfur dioxide used in making sulfuric acid comes from sulfide ores by the reaction. So they heat up this FeS2 in the presence of oxygen to generate sulfur dioxide. How many liters of sulfur dioxide measured at 983 torr in 214 degrees C are produced by the reaction of 598 grams of FeS2. FeS2 is kind of a strange one because what do you think the charge on iron is there. Well, what's the typical charge on sulfur? 2 minus, so we got 2 of them. And so the iron should be +4, right? Each sulfide is -2. But this is not sulfide. There's another sulfide ion called disulfide. It looks like peroxide. And it's like this. It's S2 2 minus disulfide. This is not one that I had you memorize, but this would be iron 2 disulfide. It's actually iron +2. This disulfide is S2 2 minus. It's also called pyrite. Look at pyrite. That's the ore. Pyrite's also called fool's gold, but this is a crystal of pyrite here. You see the nice cubic shape that crystal? It's a really pretty crystal. Yeah, it's quite a bit different. You can tell, it's definitely not gold, because gold does not form nice cubic crystals like that. But the name of this is iron 2, and it's not sulfide, because if it were iron 2, it couldn't be iron 2 sulfide. It would have to be iron 4 sulfide, but this is iron 2 disulfide, aka pyrite, aka fool's gold. Has a very nice gold luster to it. But the density of this, it's easy to tell. The density of this is nowhere near that of gold. What's gold's density? Around 20. What's the density of pyrite? Around 5. So it has like the quarter of the density of real gold. Plus gold is a metal. Metals are malleable. Pyrite is not malleable. Pyrite is very brittle. So if you try to shape these crystals into different shape and jewelry, you're not going to be successful. You're just going to break these crystals apart. So there's lots of ways that people can distinguish real gold from fool's gold just based on its physical properties. You don't even have to test any chemical properties.
Are they always perfect cubes?
No. What people will do is they'll crush this up into powder, and so it looks like gold.
Naturally occurring, is it?
Yeah, naturally occurring, it's cubes like this. When you crush this up into powder, it's like when you crush table salt into a powder, you form tiny, tiny cubes. The same thing here. If you crush these crystals up into powder, you're just going to form tiny, tiny baby cubes, basically. But yeah, it forms cubes like this. Now, when you say always, that's a difficult question to answer because, yeah, always it does, unless you can prevent it from crystallizing. And this is one of the things that I was working on. I was trying to get things to not crystallize. In other words, to form amorphous. Because amorphous have different properties. If you look at quartz crystal versus something called quartz glass, they have dramatically different physical properties. And so sometimes those amorphous materials have desirable properties that you want. But otherwise, naturally, they form nice crystals like this. I mean, if you looked at these pictures here, it's easy. These are tumbled crystals here, so you can kind of see the cubes there. Peruvian pyrite, wow, that's nice. But do you see the little cubes? this is not. This might be mistaken for gold here. Here I can see the little cubes here. This is called polycrystalline. You have lots of little cubes. You have lots of crystals. So poly meaning many crystals. Polycrystalline material. Oh, going back to this problem, let's take a look here. So if we're going to use the molar volume method, then the first step is we need to calculate the molar volume of the gas at this pressure and this temperature. That's what we'll have to do here. So why don't you calculate the molar volume, and then why don't you go ahead and complete this